is gone.
Echo is there, but it is far better.
Okay, right now, yeah, it's, I don't know where the echo comes because I muted, so there's no sound externally. Everything is in my ear. I'm using a headset, and
No problem, sir.
okay.
Your voice is clear without echo.
Yes, sir.
The
Sir,
echo happens
echo
when
won't be,
some
sir,
of us
echo
speaks.
won't be a problem while presentation, sir. It
Okay,
will happen
sounds good.
only during the question answer session. So that won't create any problem. You can continue with your what you're having right now.
Okay, all right, and you can hear me clear.
Yes.
Yes, sir.
Oh,
You are audible, sir.
perfect.
So we will start with a brief introduction.
Mm-hmm.
Sir, we'll start at 2:30.
Okay, and so the whole session is about. Can you walk me through the session? So I will talk for how long?
So 1 hour is fine.
Okay, I will try to keep it shorter because I believe 45 minutes is the maximum for an online presentation, because
Yes, sir.
otherwise the
Yes.
audience can get bored. So I will keep
Yes.
it to 45 minutes.
Okay,
And
sir.
yeah, and then it will be questions after, right?
Yes, sir.
Okay, all right.
Right. A very warm good afternoon to all the participants who have joined us. But it has to be a fine morning for our resource person, Dr. Babak Anasori. I can't start speaking without thanking our resource person to make himself convenient to contribute to our program at this odd timing. Dear Professor, heartfelt thanks for joining us. So
Thank you.
we have been running this program for about 4 days now, and this is the 8th session in this series. Dear participants, Dr. Babak Anasori will speak about the family of 2D MXene materials today. Let me introduce him. Dr. Babak Anasori received his PhD at Drexel University, Philadelphia in 2014 in Material Science and Engineering Department, which is the birthplace of MXenes. Before joining Purdue School of Engineering and Technology, he was a research assistant professor at the A.J. Drexel Nanomaterials Institute and at the Department of Material Science and Engineering at Drexel University from 2016 to 2019. He is one of the inventors of a family of MXenes, ordered double transition metal MXenes, as a result of his postdoctoral research, which was featured as one of the 2015's biggest moments in chemistry by ACS, American Chemical Society. Dr. Anasori's current research focuses on the synthesis and characterizations of novel MXenes and their metal and ceramic composites. He is one of the top 5 trending authors in the field of material science in the world, and among the global highly cited researchers 2019, recognized by Web of Science. Dr. Anasori has received several national and international awards and recognition for his research and artistic way of presenting science, including NSF Science Visualization Challenge in 2011 and 2013, Diamond ranking in ACERS Graduate Excellence in Material Science in 2012, Material Research Society Postdoctoral Award in 2016, and Emerging Leaders of 2020 by the Journal of Physics Condensed Matter. Professor, thank you for accepting our invitation and joining us. Over to you, sir.
Thank you for the nice and thorough introduction. And hi, everyone. I'm Babak Anasori. And today I'm going to talk about the family of 2D MXenes materials. Before I start talking about MXenes, and before I move forward, I just want to double check that you can hear me well and you can see my full screen. Is that correct?
Yes, sir.
Okay, perfect. So before I start about my technical talk, let me give you a brief introduction about where I'm located right now at Purdue School of Engineering and Technology at IUPUI. So first about the city. I am located at state of Indiana in the USA, which is located here, and this area of United States called Midwest. And I am in the capital of state of Indiana, which is called Indianapolis. And one of it's the third largest city in the Midwest of USA, this area. And maybe you have heard about Indy 500, which is a car racing that happens, and it's known worldwide, that happens every year in Indianapolis, which would be something interesting for engineers and specifically mechanical engineers. Now, beyond the city, the university is located at the heart of the city of Indianapolis, and it is called Indiana University, Purdue University, Indianapolis, which means that we are one of the campuses of both universities, and each department and each school either issues Purdue University or Indiana University degrees. Mechanical engineering, and in general, School of Engineering and Technology is part of Purdue University, which means that all the students and faculty are part of Purdue University, and students will receive Purdue degree in mechanical engineering. And we have a variety of different fields and departments, and that some of these are shown in this slide. And more specifically, we have a mechanical and energy engineering department, which I belong to this department. And if you are interested, as international university, you can always apply. And also, if you're also interested for a visit, we always welcome students to come for a semester for a visit to get the understanding of how the school is. And the school offers generous scholarship that you can apply, and you have to be eligible, meaning that you have outstanding academic performance, that you can get those scholarship that can cover some of the cost of your living expenses in the US in Indianapolis. So if you're interested, you can you're more than welcome to visit the websites and apply to come here for a visit or for a degree. Now, with that, I want to start the technical part of my talk. So the whole concept of my talk and the materials is based on what we can see in the future. So we know that we are living in Internet of Things, that many devices, they're all connected, many of different parts of our houses and cars, they're all connected to the internet and connected to each other. And we know that soon it won't be just having a cell phone or computer or smartwatch. Everything that we have and even parts of our bodies will be integrated in internet, with internet, that it all will communicate at all time. And that is something that we can even think of beyond Internet of Things, where we can even go beyond and have these devices in a way that we don't even wear them. They would be implanted in us. And not only these are just connected, they can do beyond that. How about if they can also create the energy for all these devices that are, for example, shirts can generate the energy, and everything else that we are carrying. So it's not that you have all these things on us. It is something that soon will be inside all these things, that everything will be integrated. Now, to get to that level, we need materials discovery. We need materials that right now we do not know they exist, because the form of the materials that we have right now doesn't really get us there. And even if with current materials or future materials, we need to get fundamental understanding of these and work on development and engineering to get to that level of technology. So these are the core of any improvement in technology. Speaking of materials discovery, one of the recent materials discovery has been two-dimensional materials. And the famous example of two-dimensional materials is graphene. Graphene is a single layer of carbon that is discovered or extracted in a single layer in 2004 based on a curiosity-driven research by these two gentlemen, Andrew Geim and Kosi Novoselov, that they basically did as a fun experiment. And this is something that I want to mention because it encourages everyone to think outside the box, not just to follow what has been done before, really go beyond what is available and come up with a new solution. And for example, graphene is a good example that has been known and has been extracted for many years. But in 2004, by using regular tape, Scotch tape, well, not regular tape, these two gentlemen were able to separate a single layer of carbon and show that they can characterize the physical properties of graphene. And that brought them a Nobel Prize in 2010. Now, mentioning that outside the box, something very interesting was that Andrew Geim also received the parody of Nobel, which is Ig Nobel, which is a fun show that has been going around for years in Harvard and MIT. That is about a research that first makes you laugh and then makes you think. And he received that Ig Nobel in 2000, because of levitating a frog. So the bottom line is curiosity-driven research with fundamental understanding and thinking outside the box can lead us to the future technologies. Speaking of two-dimensional materials, now after showing the properties of graphene, there are so many different 2D materials, such as transition metal dichalcogenides, hexagonal boron nitrides, and many more. Among these, we have MXenes. MXenes are a family of two-dimensional transition metal carbides and nitrides. So they are basically atomic layers of a transition metal that I'm showing these schematics of the atomic schematics of the MXenes, where we can have two layers. Let me turn on my laser pointer. That might be better. So there can be two layers of a transition metal, for example, titanium, with a layer of carbon in between, and the outer surface, because we have transition metal and they have to satisfy all the electrons that they need to bond, we have surface termination. Whatever is available in the environment, which is usually oxygen and humidity, which forms oxygen and hydroxyl groups on the surface of these MXenes. So what is available on the surface are all shown with this orangish yellow color, and X represent carbon and nitrogen, which is gray, and then M is transition metal. Now, you might ask, is transition metal carbides and nitrides are something new? No, they are the family of transition metal carbides and nitrides. In the bulk form, it's not something new. They have been mostly introduced in the 20th century, and they are known as high temperature materials, ultra high temperature materials, which means that some of these can withstand very high temperatures, even up to 2000 degrees Celsius. They have way higher melting temperature, even 2000, but they can get oxidized, so their oxide is still stable. They have high strengths, they're very hard, and they have high conductivity. That's why, for example, in drill bits, we have carbide or nitride drill bits because of their hardness. Also in engine turbine, we have some parts made of these ultra high temperature transition metal carbides and nitrides. Also in the 70s, in 1973, catalytic application of tungsten carbide was shown. And since then, it was a new area for transition metal carbides. Now, it is great to make bulk structures, but if you want to get to the Internet of Things, you want to get to new materials, we need to make materials at the nano scale, at the very small scale. Now, for these materials to benefit from all these properties at the nano level, it is very difficult to make these at the nano level because they are, as I said, very hard, very high temperature synthesis, difficult to make nanostructures. So these are all the carbides that are available for transition metals. Now, there has been many research going around to show that we can indeed make nanomaterials of transition metal carbides or nitrides. For example, making these cubes of molybdenum carbide at the nano scale, or making nanowires. Now, all of these are great, which is another step towards what we need to do for the advancement of technology. But what if we can really benefit from almost every single atom or every layers of single atom in the material? If we can use it at that level, then we can really pack more information, pack more energy, and control the properties, mechanical properties and physical properties at the atomic level. And that's where we get to 2D transition metal carbides and nitrides, where we have the nanostructure really at the atomic level. We're talking about 2, 3, or 4 layers of a transition metal. So moving from bulk, now we are at the 2-dimensional transition metal carbides and nitrides. Now, here's this history of MXenes. So they started in 2011, which means that before 2011, there was no mention of the name MXenes or 2-dimensional transition metal carbides and nitride. It was discovered in 2011. And since then, it expanded exponentially. It went from 1 report and 1 publication in 2011 to now, well, this is already outdated. It is 2020, but even till 2018, we had a series of discoveries that this family expanded. And we went from 1 paper in 2011 to about 3,000 papers in just 9-10 years, which is outstanding for a novel family of materials. Now, there are many papers, and even this is an editorial that I and with Professor Yuri Gogotsi wrote about the rise of MXenes that is available on ACS Nano, that it is open access, that you can go and download to get a quick, it is only 3 pages that you can get a quick background about MXenes. With the MXenes and what is available in the whole chemistry, we can cover almost the entire periodic table, which is fascinating, which means that we can really tune the properties of the material at the atomic level by controlling what elements can go in between the layers, or what elements we can use in MXenes or in their precursors. Now, enough about the introduction. Let's get to MXene synthesis and then their properties. So to make MXenes, the way we do it, unlike many other 2D materials that you can grow them at the atomic level, which is called bottom up, for the MXene synthesis, we use a top-down method, which means that we start with the bulk structure, and then we break it down to smaller and smaller until we get to atomic layers. Now, to do that, we need to do selective etching of a layered materials that has extra elements in them, which is called max phases. Now, let's look at the precursor of MXenes. So to make MXene phases, first we start with the ternary carbide, which is called max phase. And that means that they are similar to MXenes in terms of having these core of carbides, that we have 2, 3, or 4 layers of a transition metal with carbon or nitrogen. Now, in the precursor of MXenes, we have an A element, which represents group 13 to 15 mostly of the periodic table, all the red elements in the periodic table, that they bond the carbide layers together. Now, this bond is strong. It's a combination of metallic and covalent bonding, and it creates very strong bond that we cannot really use Scotch tape to break it down. For that, we need to go to selective etching that I will show in a minute. Now, how do we make these precursors? The precursor, the max phases, to make MXene, we use elemental powder. For example, if we are going to make Ti, titanium 3, aluminum, carbon 2, it's the structure of a ternary carbide. What we can do is we can mix stoichiometric ratio of the 3 elements, titanium, aluminum, and carbon. For example, here we use 3 moles of titanium, almost 1 mole of aluminum, and 2 moles of carbon. And we mix them, for example, for 24 hours. And then we put it in a control environment in a tube furnace at certain temperature, usually in the 1400 degrees C to 1700, and hold it for required time. For example, for this certain material, it's only 2 hours. And then we cool it down, and with reactive sintering, we get titanium 3 AlC2, this structure. So we go from elemental to this structure. We don't do anything. We just take it to the temperature and the conditions that this material become thermodynamically stable, and then we let the thermodynamic control the reaction and form the desired material. After we make this material, then we selectively remove that A layer that we added. For example, aluminum. We added aluminum to make these. Now, then we remove it. You might ask, why do we want to add aluminum if you want to remove it? Because if we do not add these A elements that I showed here, only using just transition metal and carbon and nitrogen, we will get the regular transition metal carbides, which are not layered, and we cannot make the two-dimensional nano-layered structure. So by introducing the aluminum, we will make this layered structure as a precursor for layered two-dimensional MXenes. After we make these, we remove the aluminum layers by selectively etching it in hydrofluoric acid, and then we get the two-dimensional MXenes. So let me walk you through the structure by using some microscopy. So we have these bulk structures where we have the transition metal, and when we have these bonding. If you look at it from the just naked eye, you will see the max phase, the precursor of MXene, is very similar to a carbide powder. It is grayish black, and this is just a photo of the powder. And if you look at it under microscope, it looks like any powder. With a closer look under scanning electron microscopy, we'll see that it has a layer structure. Going even further down by using high resolution scanning transmission electron microscopy, we see the atomic layers here. Then by putting it into the etchant, which is mostly hydrofluoric acid or something that forms hydrofluoric acid, for example, a mixture of hydrochloric acid with lithium fluoride salt, it etches selectively only certain layers. By removing aluminum from the structure, we get another grayish powder, but this time, instead of having this bulk structure, when we look, we see more open structure. And even at the atomic level, we see that they're all open, which means that we have these opening between the layers. And that's where we get to the two-dimensional. Before we had just layered, but now we have this separation, and the only bond between these layers is secondary bonding, meaning OH, hydroxyl hydrogen bonding, or we have van der Waals bonding. Now, when we have weaker secondary bonding, it is possible to break these bonding and form 2D layers. What we're looking at here is a single layer of MXene under transmission electron microscope. Then we can collect these as into a solution and make it into films or spray them. I hope that, yeah, this one video, so you can see how we make it. We have this gray powder that we put it into a solvent, and then it will get selectively etched to remove the A element. So after we leave it into etchant, then we can have the single layers of MXenes. These then we can roll it into films, or we can spray it onto different surfaces to make these coverage of nanomaterials. And they can be, we can use titanium, we can use molybdenum, we can use chromium, and when we dilute them, we have different colors, so different optical properties. We can dissolve it into different solvent, which is very important, because when you make the nanomaterial, the next step is how you can make structures or coverage out of these nanomaterials. And if they don't like to be dispersed in anything, more specifically, if they don't like water, meaning that they are hydrophobic, you will have a very hard time working with them, because they don't like to bond to any surfaces. But they are hydrophilic, they can easily get dispersed in water, and also different solvents like ethanol, acetone, and other organic solvents. We can control the single flake size, meaning that we can control whether they are 5 or 10 microns, or they are very small, like a few hundred nanometers. And by that, we can control their properties as well. Again, here is a paper size film that has been sprayed by using this solution. And here's a movie showing how just by simple spraying, we can make these films. And when we make it out of these nanostructures, they can easily stick to the surfaces, and they give a very high conductivity of 1,000 to 20,000 Siemens per centimeter. I have to mention, all of these research has been done in Ajor Drexel Nanomaterials Institute, so before I come to my current university. So, and these are all under leadership of Professor Yuri Gugotsi at Drexel Nanomaterials Institute. Moving forward, we have these MXene films that we can synthesize them, and as I said, they are single atomic or few atom layers, 1 nanometer thick layers. And obviously, like any transition metal carbide, they're expected to get oxidized, and they will get oxidized. But if we stack them, many of them over each other, then the chances of oxidation reduce significantly, and they can live a lot longer in the environment. Now, with all these synthesis, what we have is not only one element. For example, in many of for example, in graphene, what we have is a single element of carbon, and we can modify it and we can get outstanding properties. The unique feature of the family of MXenes is that we are not dealing with one element. We're dealing with 10, 11 transition metal with combination of 2 carbon or nitrogen and surface termination. We have a limitless number of compositions. Now, in MXenes, we can have 2, 3, or 4 layers of, for example, we have titanium and carbide. So here it is a Ti3C2, titanium, and carbon. We can go one step further and use 2 different metals, for example, titanium and molybdenum, or titanium and vanadium. If you use titanium and vanadium, what we get is what we expect, which is alloys, which is a solid solution composition where we mix 2 elements like titanium and vanadium, and they form these mixed structures. Another unique feature of MXene is that when we mix certain transition metals, instead of forming these solid solution, they form ordered structures, meaning that one element, for example, molybdenum, will go in the outer layers and titanium will go in the middle. So they form these atomic sandwiches at the 2D level of the carbide. So here we have only 4 layers of atoms with carbon in the interstitial sites, and we have this atomic sandwiches of molybdenum and titanium. We can even go one step further, and we have in-plane ordering, which means that we are looking at one plane of atoms where we have ordering of different elements. All of these ordering or solid solution or one element can tune the properties, which gives really a toolbox for the researchers to control the properties and really aim for the best possible outcome of the material for the desired application that I will go to talk about applications in a few slides. So to wrap this part up, what we are looking at is a 1 nanometer thick sheet of transition metal that we can control the lateral sizes from few nanometers to few microns, and they have very high metallic conductivity, so they are very conductive, and at the single atomic layer they become even transparent because they only absorb 3% of visible light per 1 nanometer, which makes them transparent. They can transport ions. That's why they have been used for energy storage application. They can absorb different molecules on their surface. They love to bond to different molecules, so they can absorb different molecules. They have hydrophilic surface, and they have a negative zeta potential, which means that the solution that we get when we have these single flakes in water, for example, it is stable. So we don't need to shake it. So when we make the ink, we can spray it at any time. Because of the negative zeta potential, they're stable for a long time. And also they have high mechanical properties, high stiffness that I will talk about later on in my presentation today. Now, based on all these things that I mentioned, this is the application chart of MXenes. This chart is available in our editorial with Professor Yuri Gogotsi in ACS Nano that I showed at the beginning of my talk, the rise of MXenes, that you can get all these plots and basically big pictures from this paper. Now, this is a pie chart based on the number of papers that published up to year 2019, middle of August of 2019, almost a year ago. And we can see that the majority of applications of MXene is around energy storage or catalysis, almost about 50%. And that means that MXenes can be used for electrochemical capacitors or electrodes for battery. And that is because they're high conductivity and also their ability to have transportation of ions between the layers of MXene. There are a lot of papers on this topic that I will not cover today because of the extensive work and many review papers that is available. And I will show you my review paper in this topic at the end of the talk that we published in 2017 in Nature Review Materials. So beyond energy storage, we can use MXenes in lasers, for example, based on their optical properties, or electronics, or in structural design, like mechanical, because of their mechanical properties, or making composites. That this is the part that I will mostly focus because of the interest in mechanical engineering and your interest. Also, there are studies about biomedical application of the same material. So you're looking at the same material that has all these applications. You can put it in battery electrodes. You can put it in laser. You can put it in composites for improving the mechanical properties, or we can use it, for example, for dialysis, because they can absorb ions and they can absorb urea on the surface of MXene. In electromagnetic area, MXene showed the best performance of electromagnetic interference shielding and even antenna, that I will cover also this part for the interest of the audience, also environment, sensors, and many more. Excuse me, I need a little bit of hot water because it's only 5:30 a.m. here. So moving forward, optical properties. As I said, MXenes have a really large range of optical properties, which means that they can have different absorption peak in the UV-Vis region, and they can be used for a variety of applications. For example, because of this, they have been used for cancer treatment, for photothermal therapy, which is, again, another topic, and I don't want to get to biomedical because of the interest of the audience today. So beyond optical or biomedical application, electromagnetic waves interaction. If you open our cell phones, we see all these black areas in the cell phone. So one part which we take it for granted is these black are not really just, many of these are just plastic. They have some materials in them. It can be nanomaterials or carbon that they prevent noise coming from one device or one component to another. Because when we have electricity, when we have current, we know that we can create electromagnetic waves, and that if it comes from one component, it can interfere with another one. So we need to prevent, we need to encapsulate every component that the electromagnetic waves do not come out and interfere. And that is something called electromagnetic interference shielding. In a paper that we published in 2016 at Drexel University with collaboration with KIST, Korea Institutes of Technology, we showed that MXenes and their polymer composite, they can outperform other materials in electromagnetic interference shielding. So by just using a solution of MXene that I talked about earlier, that we make it, we have the nanomaterial in water, and then we spray it and make a film. This film, or we can mix it with polymer and make a film. So we see that, for example, here we have polymer in between the layers. By doing that, we can have a polymer MXene composite. We can control the mechanical properties and also make it more stable in environments. All these can be used for electromagnetic interference shielding. So we can use MXene in those black area that I showed in the picture of the cell phone. And we showed that by using MXene, we can get the same level as known metals, such as aluminum and copper, as known as the best electromagnetic interference shielding material. Now, the advantage here is that we are working with already available in solution nanomaterial, which is very important, which takes me to the beginning of the talk, that if you want to get to beyond Internet of Things, we cannot simply use what is available, which has been available to us, for example, aluminum and copper in the bulk form. Because if you use the bulk form, there's nothing wrong, but we can never get to the nano level, invisible level, where we can have a cell phone smaller and smaller, or even devices integrated in our garment, in our clothes, or even in our bodies. So to get to the same level of performance, we need nanomaterial. And MXene showed that they can outperform other nanomaterials and be at the same level. Very recently, Professor Gogotsi at Drexel University with Korea Institute of Technology, they showed that MXene can outperform even metals. So we are getting to outperforming any known material for electromagnetic interference shielding. The same interaction with electromagnetic waves, we showed that MXene antennas can also outperform other nanomaterials and work at the same level of metals like copper, which is another important milestone here, because by using these, we can simply spray, making almost transparent antennas. So this is just an example. This is a regular dipole antenna that we use just as a proof of concept in our first publication on antennas. And we showed that just by simple spray on a transparency sheet, we can make these antennas, and they are very easy to fabricate, and they can be on any surface, and they outperform other materials. So again, one step towards Internet of Things, towards a future, by making these very thin, almost invisible antennas. So I talk about electromagnetic shielding and antennas as this part. And then more related to the topic of mechanical engineering, I will go to structural part, which if you look, we only have about a very small pie of all the applications of MXene. This is about 5%. The reason for this is because this is just a novel material, and they have not really been explored for mechanical properties or composites. But I will show you MXenes have a very high potential for usage in composites and improving mechanical properties, which gives us a really great area for exploration. So it means that we can explore novel composites and explore their properties, and not just to make stronger body of the car. Because of all these properties that I mentioned, for example, high metallic conductivity and also capability of storing energy, it's not only to make just stronger body. These are all not related to MXene. These are all studies and different concepts from different car makers, that we can basically put the battery, for example, in the body of the car. Imagine how much more energy we can store if we use the body, all the area of the car. That right now, for example, if you look at an electric car, we have the battery, and then we have the rest of the car. Now imagine that we integrate everything together, that the rest of the car is also where we can store energy. Just imagine how much more distance we can drive with a car if we use everything we can, for example, all the unused body or under the hood or in the trunk, all into battery part of the car. To take it to that level, we need nanomaterials that they're multifunctional. They're strong, at the same time they can store energy. And storing energy in the battery means that they can have ions going in and coming out. And there are many concepts car, and there are even some, for example, MIT and Lamborghini, they're exploring using these carbon reinforced body of the car for energy storing in the body. So there are concepts and there are some research, and we believe MXene can be one of the nanomaterial candidates for this application. So more on the mechanical properties. So as a transition metal carbide, MXenes have very high stiffness. The stiffness can be in the range of 3 to 400 gigapascal, which if you look at all the known materials, the highest Young's modulus of all materials is for graphene, where we have 1000 gigapascal or 1 terapascal of Young's modulus. After that, we have hexagonal boron nitride. And right after that, we have MXenes. Now, these are all measured on a single atomic layer of few atom thick of MXenes. So this is done by using atomic force microscopy on a flake of MXene that we went with collaboration with our collaborators from Drexel and University of Nebraska, Lincoln. We went and really pushed one single layer of MXene to measure its two-dimensional modulus and convert it to Young's modulus by considering the thickness. And we found that MXenes are the third strongest material. And now one unique feature is that if you're looking at graphene and hexagonal boron nitride, these are the values that we can get only if we grow a single layer, which from a mechanical engineering perspective doesn't really help us, because we do not need just a single layer. We need a lot of material to put it in the composite. So it is great to have this very high Young's modulus, but can we put it in our composites? The answer is no, because we only have a single layer. And also this is not even hydrophilic, so it means that it has very hard time to get bonded to other material. Now for MXenes, this is the one that we can make in large quantity. It is very similar to graphene oxide or reduced graphene oxide, but if you look at the numbers, when we go from graphene to graphene oxide, we go from 1000 to 200 gigapascal. Now, that's where MXene outperforms all other solution processed 2D materials or nanomaterials that we can make in large scales, and they are hydrophilic, ready to bond. Also, even beyond, MXenes, as the nature of transition metal carbide, if they are in controlled environment, they are high temperature materials. So we can integrate them, we can put them in metals, can put them in ceramics, possibly, and then use them for high temperature applications, which is the nature of transition metal carbides. Now, has anyone done it? Very few. For example, just looking at MXene Films, this is a study, again, published at Drexel and their Australian collaborators, that showed by using just MXene Ti3C2, we can make large scale production, and just the film of these, which is only 1 micrometer thick. So see, we're looking at the cross section of this film, that is only 1 micron thick, we can get very high values. For example, tensile strength of just this film reaches up to about 500 megapascal of these films, 1 micron thick. And these are not really sophisticated production. We have the MXene, and they just use a blade to flatten it to make these films. They have very high conductivity, up to 15,000 Siemens per centimeter, and they outperform many materials in electromagnetic interference shielding that I mentioned earlier. I mentioned. Hello?
So it was just a disturbance. Carry on, sir, please.
I'm sorry, are you talking to me?
Yes, sir. It was a disturbance.
Okay, can you hear me now?
Yes, sir. Yes.
Okay, did you see this previous slide?
Yes, sir. It's
Okay,
fine.
all right. So yes, please feel free to stop me if you do not hear me, because it's just the reality we are living in, and with virtual and internet. So just feel free to stop me at any time needed. So this is just pure MXene that we get these outstanding mechanical properties. Now we can simply integrate MXenes in different composites. For example, we can make polymer MXene composites by just mixing. So we have this solution of MXene, and we just mix it with polymers and make MXene polymer composites. Or we can make ceramic and metal MXene composites by mixing MXenes with metals or ceramics and make these. This is an area that I believe has a lot of room for improvement, and very little has been done. For example, for ceramic MXene composites, this is a research that we did at Drexel with collaborators at Pennsylvania State University, that shown that by mixing MXenes with zinc oxide, the 2D flake of MXene will go at the grain boundary of this oxide ceramic and cover and wrap around these zinc oxide particles. Then by sintering only at 300 degrees C with 250 megapascal, we can get almost to, so this is the relative density, we get almost to 100 or slightly less, like 96% dense of the composite. The other advantage is by wrapping these MXenes around the grains of the ceramic, we prevent grain growth. So instead of having something like this during the synthesis, we keep the grains at a lot smaller, and we prevent the grain growth because we don't allow the diffusion happen by putting a MXene layer in between. And here's a transmission electron microscopy image that shows that we can indeed put MXene flakes at the grain boundary. By doing that, we can improve hardness, and the measured modulus by nano indentation also showed some improvement. So this is in ceramic composite. There are only very few papers on this topic, and there's a lot more room for improvement of MXenes composites. Also for metal composites, the same thing. There are very few papers, but we can make, here's one example of making magnesium MXene composite. This is with collaboration with Drexel and University of Chicago. And we showed that we can put MXenes in magnesium alloys, magnesium lithium alloys, and they get a good dispersion, and it can improve the properties. Now, you might say, well, we can also put titanium carbide instead of going to the route of MXene, just simply put titanium carbide. Yes, we can. But the advantage here like all this previous slide that I mentioned, here we're talking about only 1 nanometer thick of these additives and reinforcing materials. So, for example, here we're only talking about half a weight percent to maximum 5 weight percent. We can see, and I believe 5 weight percent is already too much. We have to keep it within below 1 to maximum of 2 weight percent. The reason for that is we only need just 1 nanometer thick of these around the particles. Here's a good example. If you go beyond 1 to weight percent of MXene, densification drops because then we get too many of these. So we can make the composites that right now we are making with the regular bulk materials of oxides with transition metal carbides. But instead of using 5%, 10% to improve the mechanical properties, we only use maybe barely 1 weight percent. So it doesn't change the density, it doesn't change the mass, but we can significantly improve the mechanical properties. So this is one of the big advantages. At the same time, we can have a uniform distribution of the reinforcement in the matrix, because it's not just random particles in the matrix. We can have it wrap around different particles. So we have a uniform distribution. And by having these layers, we can not only improve the strengths, we can also improve toughness because of crack deflection. So we are combining all the benefits by using these MXenes instead of just adding particles to hope that we can improve the strengths of the material. So, and that's the area for composites more related to mechanical engineering. The bottom line is we have a very large family of materials that we barely scratch the surface. So these are all the solid ones are the ones that have been synthesized. Just look at how many more possible compositions we can fabricate, and we have not fabricated yet. So there's a lot more room for improvement. When we consider alloys, salt solution, we get a lot more of possibilities. Ordered phases, another area that none of these have been synthesized, are waiting for the scientists and researchers to make these possible. And by combining all these, we can target different applications. And because we are working at 2D level, at 1 nanometer thick, playing with these elements will significantly change the properties. In bulk, usually we don't see this effect because we have several layers, millions and billion layers of atoms. Here, because we're dealing only with 4 layers, every changes in composition easily will be visible in all the properties, including mechanical properties, energy storage, electrical properties, and others. And we can all work on this field and create what is needed for the future of our technology. Now, before I finish, I also want to invite everyone. This is not related to MXene. This is NanoArtography, a science as art competition. That if you are using electron microscope, like scanning electron microscope, or just microscope, and you can capture nice visuals, then turn it to a piece of art by maybe colorizing these. So looking at here, these are all actually made in black and white, and then the student add colors and turn it to art. We can make these and submit it to NanoArtography. This is the website, nanoartography.org. And you have until end of September to submit, and there's a chance of winning cash prizes of $700, $500, and $300. In the past few years, we had many submissions from India, and even the first place of 2019 was from India. So it is open to everyone, and submit your image now for the chance of winning these. And please also encourage your students to visit nanoartography.org to learn more about this great opportunity. And it will bring a lot of visibility internationally for your work around the world. So with that, I would like to thank my research group, who helped me in mostly making the schematic, and also Drexel Nanomaterials Institute and Professor Yuri Gogotsi, because that's where I did all these research before I joined Purdue School of Engineering at IUPUI. If you are interested in MXene, you can read the Nature Reviews Materials review article that we published in 2017. And also, we have a book on MXenes that is obviously titled 2D Metal Carbides and Nitride MXenes that I co-edited with Yuri Gogotsi, that is published by Springer Nature, and you can download that. And if you are more interested in double transition metal MXenes, you can download our recent review paper on this topic from my research website, which is myfullname.com, and go to the papers publications page, and you can download this manuscript, which is available online on my page. With that, I'm open and happy to answer any questions. Thank you.
Thank you, Professor. It was a wonderful session. Honestly, sir, is it audible?
Yes, yeah.
Yes. Thank you, Professor.
Sure, yes. My pleasure.
Honestly speaking, I was never aware of MXene materials until you told me you're going to speak about the family of MXene materials. To be frank, I was even perplexed about how to spell this word, MXene. But Google came to my aid.
Great. Yes, yeah, I know. It's the way we write it and we pronounce it is also different. Many people who are not familiar, obviously, even Google sometimes or Word recommend saying MXene, but we pronounce it MXene, and I hope that now you understand why, since it is made from max phases.
Sure, sir, sure. Fine. Shall we move to the question and answer?
Please, yes.
Yes. There is one question from Anis KJ. Whether MXene material or MXene metal composite are produced commercially anywhere?
That's a very good question. That's exactly an engineering question, because sometimes we get so focused on the science that we forget that, okay, it is great, but can we make it in large scale? For just pure MXene, we have to remember that these are only almost 10 years old material. So usually getting it from lab or discovery to commercial usually takes 10 to 20 years. The good news is now, because of all the advancement in all technologies, it is a lot faster. And MXene is one of the materials that we are moving to commercialization in only less than 10 years. So there are companies now that they are making I'm talking about pure MXenes. They're making MXenes now available. One example is there are many companies that they sell MXene, just MXene, but for applications, there's a company. One example is the Japanese company Murata, who's we worked a lot before with them, and now they are making. Right now, they have a pilot scale that they can make 1 kilogram of nanomaterial per day. And I have to mention, 1 kilogram is a lot. For example, with 1 or 2 grams, we can cover the entire. I use more American football field. So with only 1-2 grams, we can cover a large surface area. So 1 kilogram is a lot. So we are moving to commercialization of just pure MXene now that is available to make it. Talking about composites, like metal composites or ceramic composites, we are at the very beginning. There are only few papers, 3-4 papers on metal composites and 3-4 papers maximum on ceramic composites. So there's a lot of engineering need to be done before we get to commercialization. And that's the area that as engineers, as researchers, we can contribute. So this is a new area. We have the material. We need to make the composite to explore it for different applications. So metal composite of MXene has not gone to commercialization, and even a lot of research needs to be done before we get to that level.
Sir, another question from Manoj Balakrishnan.
Sure.
Is it possible to use MXene-Ceramic Composites in place of existing composites for extreme temperature applications, like in aerospace?
That's a very good question, and it is also a question very close to my heart and my research area. Right now in my lab with my students, we are exploring MXenes with ultra-high temperature ceramic composites, and they have not been explored yet, but we believe because MXenes are transition metal carbides, and transition metal carbides are one of the three categories of ultra-high temperature materials, being as borides, carbides, and nitrides. We believe that we can integrate these in bulk borides and use them for ultra-high temperature materials. Is there any papers on this topic? No. Will it be? Hopefully soon, if everything goes as planned, and hopefully we won't have any more shutdown of the labs. Hopefully within a few months, or a maximum of hopefully in 2021, you can find papers on this topic that will be published from my lab. So you can check my website and stay tuned, or we can even communicate later via email. So hopefully soon in 2021, we'll have papers on exactly this topic, which is very interesting.
That's good to know, sir. Sir, you mentioned about electromagnetic pollution. So the next question is related to that. Is electromagnetic shielding related with SAR value in cell forms? So what is the advantage of MXene in comparison with the existing materials is the question.
That's a great question, because always if we are competing with what is available, we have to see what are the main advantages. The main advantage that I mentioned is one, about a nanostructure. So instead of making, for example, using a thick film, something that is even less than a millimeter, is a lot of space in a cell phone that we're talking about only a few millimeters. So we need to come up with materials that we don't really take in space. So we can use only a few nanometers instead of few millimeters. So one advantage is thickness. The second is the ease of processing. That, for example, if you want to make, because you can make also nanofoil of aluminum, or we can use nano silver. But as a metal, to make it to nanofoil, it is very challenging to keep a foil at that level without ripping. Or making nanomaterials like nano silver, it is very difficult to make it dispersible, because metals, unlike MXenes, they don't like to get dispersed in any solution, right? So that's why we always need to shake, for example, even paint, although they have a lot of surfactants that they are stable, but we need to shake it to get a uniform dispersion. For MXenes, they are hydrophilic, they are stable because of their negative zeta potential, and they can bond to different surfaces. So the bottom line is, it is the ease of production when we get to make different electromagnetic shielding, and also the performance. The 2020 paper published in Science just this past month by Drexel Group and KIST, Korea Institute of Technology, showed that MXene outperforms any other material, even metals. So the other advantage is MXene is simply better in electromagnetic interference shielding compared to any other material.
Sir, another question from Martin Anthony. He's asking, how are computational simulations for nanomaterials done?
So that's a very good question. For MXenes, there are at least, if not more than half of the publications, thousands of publications on computational sites. because as I showed in my slides, we have a very large family of 2D materials, and we cannot do just experimental. There are a lot of computation that in many cases can guide the experimentalists, like myself and like my group, that we only synthesize and work with materials. The computation can be done with, for example, first principle, like density functional theory, or MD, molecular dynamics, to explore, for example, larger scale of MXenes. There are many papers, there are many also review papers that they look at only the computational side of this large family of materials that you can download and learn more about these. We have chapters in MXene book that that you can read and learn more about the computational side of MXenes.
Sir, one more question from Sai Supriya Lakshmi. She's asking, MXenes are made by, when MXenes are made by spraying, are there any problems encountered while ejecting the films? And is there any loss in structural properties while rolling of MXenes sheets?
So that's also a very good question, because it mainly first, whether it will be a loss from spraying to rolling, it depends on the design, because the main part of the mechanical properties, if you remember from my beginning of the talk, the bonding between the layers of 2D flakes is secondary bonding. So it's van der Waals bonding, so it's not as strong as metallic or covalent bonding. So if we can control this bonding, we can improve the mechanical properties. Also, it depends how these 2D flakes are oriented. So if you have a random orientation, or if we have not perfect layering of the flakes, we have lower mechanical properties compared to where we get perfect stacking of the 2D flakes. So design is very important. We can get very perfect stacking with both rolling and spraying, and we can get awful stacking with both methods. It depends on how. So this is really an engineering part that we need to more work on. We know that we can get very good stacking in both methods, but if you don't do it right, we can really get low mechanical properties. So it is a matter of engineering in making stronger or weaker films. I think also there was a beginning of the question I forgot. What was the question at the beginning? What was the question? I forgot the first half of the question. What was the first?
How difficult is to retrieve after spray painting of material?
So for spraying, you can think of these MXene inks as simple paint. You have spray paint the same way you can paint on different surfaces, on different structures, on even paper. We can do the same thing with MXene. So it's exactly identical to spray paint. Anywhere you can think of spraying spraying just a paint, you can use MXene paint to paint a conductive coat that can be your electromagnetic interference, can be your antenna, or even can be your battery electrodes or your composite.
Sir, one more question. I have read somewhere that MXene is used to create highly conductive clay. So what is the significance of that discovery?
So yes, so that is basically where we discussed. So that started in 2014. A paper published in Nature in 2014 that at Drexel, both Professor Michel Barsoum and Professor Yuri Gogotsi collaborated and showed that MXenes are conductive clay. So what the significance is, clays, in general, clay material, they are oxides. right? So we have a large, so all these transition metals and metals, they're all like, they're all bonded with oxygen, which means that they're non-conductive. They're not conductive at all. But by using the MXenes, by turning oxides to carbides, now we have high metallic conductivity. When we have something that we can work, so we discussed spraying in the last question, previous question. Now think of something that you can work with as simple as mud, as clay, that you can just add water and then form it into any shape you want, and then you have that. You can have that shape and use it. That's a clay. Now imagine you can make your antenna with that clay. Imagine you can make a composite with that clay. Imagine you can even possibly make that ultra high temperature ceramic with that clay, that you just think of clay, think of mud, that you mix it with different metals or different particles, and then you form it into desired shape, and then you can put it into furnace and sinter everything together. It's this ease of use and its unique mechanical and electrical properties, which makes it significant as clay. Excuse me.
Okay, thank you, sir. There are no more queries left. Thank you for accepting our invitation and joining us today. We are deeply obliged. It has been a pleasure hosting you, sir. Wishing you a good day ahead.
Thank you. You have a good day too.
Thank you,
Bye,
sir.
everyone.